So let's take a look at an example. We have a matrix A. We want to find the determinant of the matrix. Now, it's just a 3 by 3 matrix. We know how to find the determinant of a 3 by 3 matrix, and at this point, we can probably do so quickly. But let's get some practice in using elementary row operations and seeing how we can use those to find the determinant of a matrix. Okay? The idea here is we're going to take our matrix A and we're going to use elementary row operations to transform matrix A into something that is easier to find the determinant of. And once we do that, we can invert those elementary row operations, use what we know about how elementary row operations affect the determinant, and find the determinant of the original matrix A. Okay? So step one, we want to transform matrix A using elementary row operations into something that's easy to find the determinant of. Now, we've already seen triangular matrices are super easy to find the determinant of. So if I could have, say, my non-zero elements of the matrix to be just above the main diagonal and below that main diagonal to be all zeros, that'd be real easy to find the determinant of. But of course, if it's in that form, it would actually be in row echelon form, wouldn't it? So what we want to do here is we want to get matrix A into row echelon form. If you want to, you could go all the way to reduced row echelon form, but we don't really need to go that far in order to get a triangular matrix. Okay? So let's start with matrix A. And I just want to get to row echelon form. We don't need to go all the way to reduced row echelon form. We do, though, need to keep track of our elementary row operations. So we can't just plug this in to a calculator to take us all the way to reduced row echelon form, because usually a calculator doesn't tell you the steps you use to get there. Okay, so we're going to have to do this by hand. So I've got a leading entry here. I want zeros below it. That's my goal here. I've already got a 0 in row 2, so I need a 0 in row 3. So what I'm going to do is I'm going to take -1 times row 1. I'm going to add it to row 3. That'll be my new row 3. Okay, and so I leave row 1 the same. And actually, just knowing what I need to do later, I'm going to actually move this over a little bit. Because remember, I said we're going to want to invert these row operations. So just let me leave some room so that we could write the inversion over here. And hopefully that'll be clear in a moment what I'm trying to do. Okay, but for this elementary row operation, I'm going to leave row 1 the same. I'm going to leave row 2 the same. I'm just changing row 3. And I'm just going to take negative row 1 plus row 3. So -2 plus 2 is 0. -1 plus -1 is -2. And +1 plus -1 is 0. Okay, so far so good. I still don't have that stair-step pattern. So I'm going to go one more row operation here to get a 0 down here. I'm going to take negative. Actually, you know what? I really like this 0 right here. And partially just to make this example interesting, let's swap row 2 and row 3. So I'm going to leave row 1 the same. Row 2, I like the 0, so I'm going to swap row 2 and row 3. And also I notice everything in row 2 is divisible by 2, so let's do that also. So I'm going to multiply row 2 by -1/2. That'll be my new row 2. Now, part of the reason why I'm doing this is actually I'm making the problem just a little harder, adding a couple row operations, because I just want to show you an example of each row operation. You could actually get to row echelon form without some of these operations. Okay? But now that we're here, I'm going to take 2 times row 2. I'm going to add it to row 3. That'll be my new row 3. That'll give me a 0 right there. So let's leave row 1 the same. Row 2 stays the same. Row 3 becomes 0. And then 2 plus -2 is 0. And then 0 plus 3 is 3. Okay? And at this point, we are in row echelon form, right? We've got that stair-step pattern. Our matrix is an upper triangular matrix, which means it's easy to find the determinant of. Okay? So the determinant of this matrix here, let's call it, you know what, I'll just write the determinant over here. So actually, let's name all of these. So this is A. And let's just give them subscripts. This is A1, this is A2. So the subscript just illustrates how many row operations we've done. So we did 4 row operations to A to get to A4 here, and we can easily identify the determinant of this last matrix A4. It's a triangular matrix, so I just multiply the entries along the main diagonal. 2 times 1 times 3 is 6. Okay, now what I want to do is I want to work my way back up to find the determinant of matrix A, using just what I know about how elementary row operations affect the determinant. Now to do this, I have to invert the row operations I have. Okay, so how do I go back? Well, if I want to, here I added twice row 2, so to invert it, I need to subtract twice row 2. Okay. So then how would that row operation affect A3, affect the determinant of this matrix? So if I add a multiple of one row to another row, remember the determinant doesn't change at all. So going from A4 to A3, using this elementary row operation, the determinant is going to stay the same. It's going to stay a 6. Okay? How about going from A3 to A2? So in order to go from A3 to A2, I need to invert this row operation. Here I multiply by -1/2. The opposite of multiplying a row by -1/2 is multiplying a row by -2, right? So -2 row 2 is my new row 2. Okay, so what does this row operation do to the determinant? If I multiply a row by a non-zero constant, the determinant gets multiplied by a non-zero constant also. So the determinant of my new matrix A2, of this matrix A2, which I can get to from A3 by using this elementary row operation, I'm going to take the determinant of A3 and multiply it by -2. So I get -12, right? 6 times -2 is -12. So hopefully you see what we're doing here. We started with a matrix that was easy to find the determinant of, and then because the inverse of an elementary row operation is also an elementary row operation, I could think of how those elementary row operations that help me get back are going to affect the determinant. All right, let's keep going. How do I go back from matrix A2 to A1? What elementary row operation would I do? How would I invert swapping two rows. Well, if you want to undo swapping two rows, you just swap them back. Okay? So how is that going to affect my determinant? Well, if you swap two rows, that elementary row operation just changes the sign of the determinant. So the determinant of A1 is going to just be the negative of the determinant of A2. And the determinant of A2 was negative 12, so negative 12 is going to be positive 12. Okay? All right, we're almost there. We're almost back to our original matrix A. So I need to invert one more elementary row operation. I took the negative of row 1, added to row 3. That was my new row 3. So if I added negative row 1 to row 3, in order to invert this, I need to subtract negative row 1 from row 3. Okay? Or add positive row 1 to row 3. So row 1 plus row 3 into row 3, that's going to undo this elementary row operation. Okay? Now, what kind of an elementary row operation is this? This is adding a multiple of one row to another row, right? 1 times R1 plus R3. That elementary row operation doesn't change the determinant at all, which means the determinant of my original matrix A is going to be the same as the determinant of my altered matrix here, A1, which was 12. Okay? So the determinant of matrix A is 12. And we were able to do that without doing that laborious determinant calculation, but by using elementary row operations and by finding the determinant of a much easier matrix and then working our way backwards using what we know about how elementary row operations affect the determinant.